We saw that the von der Waals equation was introduced to achieve a better description of the behavior of real gases than the one provided by the ideal gas law. This equation of state is derived from the von der Waals approximation characterizing the opposite intermolecular forces by a long-range attractive and a short-range repulsive potential, as already presented in the plot of the net potential energy of the von der Waals forces versus the molecular distance r. Based on this approximation, von der Waals constructed a cubic equation in terms of the volume of gas, where the pressure P of the gas is equal to the gas constant R times the temperature T of the gas over the difference between the molar volume Vm of the gas and its volume correction constant B, minus the pressure correction constant A over the square of Vm. The correction constants A and B are the parameters in the equation of state specific for any substance modeled as a von der Waals gas or fluid. The first term in the right-hand side of the equation of state is responsible for the volume correction for the volume excluded by the molecules due to the repulsive intermolecular forces, which is also called the repulsion term of the von der Waals equation. The role of the second term is the correction in pressure due to the attractive intermolecular forces, and it's also known as attraction term. As a result, the pressure in the equation of state can formally be written as the sum of two terms, the pressure attributed to the repulsive intermolecular forces and a negative pressure correction term due to the attractive intermolecular forces. In this model, the repulsion term depends on both the temperature T and the molar volume Vm of the gas with the volume correction constant B, whereas the attraction term depends on Vm and the pressure correction constant A. Because the von der Waals approximation describes the behavior of real gases only with a limited accuracy, several modifications were constructed to improve the von der Waals equation. Here we present some of the most popular examples proposed over the last few decades, which can be divided into three groups. The first group consists of those equations of state where the pressure correction is improved in the attraction term of the von der Waals equation. In these modifications, the denominator of the attraction term remains quadratic in the molar volume. That is, the improved equations of state remain cubic in the volume of the substance. In the case of the second group, the volume correction formula is modified in the repulsion term of the von der Waals equation, which results in non-cubic equations of state. Evidently, those improved equations of states belong to the third group where both the pressure correction and the volume correction are modified. That is, there are some improvements in both the attraction term and the repulsion term of the von der Waals equation. We start with the short overview on several cubic equations of state which are frequently used in thermodynamic calculations. The first cubic equation we will present is the Redlich-Kwong equation of state, where the attraction term also depends on the temperature and the pressure correction involves the volume correction constant. Then we will talk about the Soave-Redlich-Kwong equation of state, where the temperature dependence of the attraction term has a more general form, and the acentric parameter omega is introduced to accommodate the effects of the deviation from the spherical symmetry of the molecules interacting each other in the real gas, vapor or liquid. The next equation of state we will present is the Peng-Robinson equation, which follows a similar strategy by keeping the acentric parameter but applying the volume correction parameter more extensively in the attraction term. We will also consider its improvement called the Peng-Robinson-Stryjek-Vera equation of state, where an adjustable empirical parameter kappa-1 specific for substances with some temperature dependence is introduced in the attraction term. The last cubic equation of state we talk about is the Patel-Teja equation, where a third parameter C is introduced in the attraction term of the equation, providing substance-specific critical compressibility factors based on experimental data. Then we will present three non-cubic equations of state where only the repulsion term is modified, starting with Guggenheim's equation of state. In this equation a more accurate model is provided for the hard sphere interactions between molecules, and some experimental data are applied in the thermodynamic calculations with the repulsion term as well. The next non-cubic equation of state we will consider is the Carnahan-Starling equation, where a more accurate representation of the hard sphere interactions is achieved by applying the virial expansion of the repulsion term with a closed formula for the expansion coefficients. The last equation of state in the second group we talk about is the Boublik equation of state, where the hard sphere geometries of the interacting molecules are generalized by using non-sphericity parameters in the attraction term. Finally, we will present three examples in the third group, starting with the equation of state derived from the simplified perturbed hard chain theory, which still applies the Carnahan-Starling approximation in the repulsion term and uses a theory unifying polymer solution theories and the perturbed hard sphere theory to model the molecular interactions in the attraction term. Then we will talk about the Christoforakos-Heilig-Franck equation of state, providing a generalized expression of the Carnahan-Starling equation for the repulsion term and applying a square well potential model for molecular interactions in the attraction term. The last equation we will consider here is the Deiters equation of state, which still uses the Carnahan-Starling approximation in the repulsion term but applies a semi-empirical description of the square well potential model in the attraction term. In order to be able to compare the different equations of state that we will present here, we will introduce some conventional notation frequently used in this context. We derive several relations between the von der Waals constants A and B and the critical constants of a gas, and we will use two of them here. The first relation tells us that the pressure correction constant A can be written as 27 times the square of the volume correction constant B, times the critical pressure Pc of the gas, and the second one states that A is given by 27 times B over 8, times the gas constant R times the critical temperature Tc of the gas. If we express the constant B from the first relation and substitute it into the square of the second one, then we obtain A in terms of the critical constants, which can be inserted into the first relation to express B in terms of the critical constants. As a result, the von der Waals constants A and B can be written as omega A times R squared times Tc squared over Pc, and omega B times R times Tc over Pc, where the constants omega A and omega B are equal to 27 over 64 and 1 over 8, respectively. Now we start with a cubic equation of state introduced by Redlich and Kwong in 1949 to improve the von der Waals equation, which is an empiric formula with a modified attraction term. In this equation of state, the denominator of the second term correcting the pressure becomes temperature dependent, and it is given by Vm times the sum of Vm and B, times the temperature T raised to the power 1 over 2. The parameters of Redlich-Kwong equation of state are still the pressure and volume correction constants A and B of the gas, and they can be expressed in terms of the critical constants of the gas from the vanishing first and second order derivatives of the pressure with respect to the molar volume evaluated in the critical point of the gas. As a result, the pressure correction constant A is given by omega A times R squared times Tc raised to the power 5 over 2, over Pc, whereas the volume correction constant can be written as omega B times R times Tc over Pc with the constants omega A and omega B that are equal to 0.42748 and 0.08664, respectively. These numbers are values of the fractions containing square roots of integers that appear in the solution of the equations obtained from the vanishing first and second order derivatives. The critical compressibility factor Zc of the gas can also be determined from these equations supplemented with the definition of Zc. For the Redlich-Kwong equation, Zc is given by 1 over 3, which is a value closer to the typical values of Zc for real gases than 3 over 8 obtained from the von der Waals equation overestimating them. The compressibility factor Z of a gas can be derived in terms of its state variables from the improved equation of state as well, and expressed by 1 over 1 minus h, minus capital A squared over capital B, times h over 1 plus h, where the square of capital A is defined by A over R squared times T to 5 over 2, capital B refers to B over R times T, and h simply denotes B over Vm. Redlich and Kwong compared the prediction of the modified equation of state with the one of the von der Waals equation for the measured data of the compressibility factor of ethane as a function of its reduced pressure, demonstrating the improvement produced by the temperature-dependent pressure correction in the equation. By applying the equation obtained for the compressibility factor, the natural logarithm of the fugacity coefficient phi of a real gas can also be calculated, and it can be written in the form Z minus 1, minus the natural logarithm of the difference between Z and capital B times P, minus capital A squared over capital B, times the natural logarithm of 1 plus capital B times P over Z. The Redlich-Kwong equation of state allows one to reliably calculate the critical properties for various substances, predict both vapor and liquid properties, and describe high-pressure phase equilibria for both pure gases and binary mixtures. The Soave-Redlich-Kwong equation of state was introduced in 1972, when Soave suggested a more general temperature-dependent attraction term in the Redlich-Kwong equation. Instead of the temperature T raised to the power 1 over 2 in the denominator, he applied a temperature-dependent function called alpha function or cohesion function in the numerator with a third parameter omega besides the correction constants A and B. This parameter is called eccentric factor, describing the deviation of the reduced vapor pressure of a substance from its pressure in fluid phase, and it is associated with the shape and polarity of the molecules, measuring their deviation from spherical symmetry. The alpha function is derived from the fit of the experimental values of the vapor pressure of pure substances, where the square root of alpha is plotted against the square root of the reduced temperature measured for a number of hydrocarbons. Because the data points for each substance with given critical constants form almost straight lines passing through the point where Tr and alpha are equal to 1, Soave used a linear approximation. He expressed alpha raised to the power 1 over 2 by 1 plus the slope m of the line obtained for a given substance times 1 minus its reduced temperature Tr raised to the power 1 over 2. by applying the definition of the eccentric factor omega stating that the reduced saturation vapor pressure at the reduced temperature of 0.7 is equal to 10 to the power minus 1 minus omega, the alpha function can be evaluated at the same reduced temperature. Because the straight lines must pass through the point given by this reduced temperature and the corresponding value of alpha, the slope m can be determined as a quadratic polynomial of omega. Here the pressure and volume correction constants A and B expressed in terms of the critical constants have the same form as in the case of the von der Waals equation of state, but the constants omega A and omega B are equal to those of the Redlich-Kwong equation of state. The critical compressibility factor is also the same, that is Zc is given by 1 over 3. The compressibility factor as a function of the state variables is obtained by solving the cubic equation of Z derived from the Soave-Redlich-Kwong equation of state, which states that Z cubed minus Z squared plus the quantity of capital A minus capital B squared, times Z, minus capital A times capital B, is equal to 0, where capital A denotes A times alpha times P over R squared times T squared and capital B is defined by B times P over R times T. In the general case this equation has three distinct roots where the maximum of the roots gives a compressibility factor of the substance in the vapor phase and the minimum corresponds to a value of Z in the liquid phase of the substance. The same cubic equation of Z can also be given for the Redlich-Kwong equation of state, but the definitions of capital A and capital B are different. As a result, the fugacity differs from the one obtained for the Redlich-Kwong equation, and the natural logarithm of the fugacity coefficient phi of the gas is given by Z minus 1, plus the natural logarithm of the difference between Z and capital B, minus capital A over capital B, times the natural logarithm of 1 plus capital B over Z. Since the Soave-Redlich-Kwong equation is based on the fitting of the measured vapor-liquid curve, it is able to describe the phase behavior in the critical region better than the Redlich-Kwong equation of state. The modification introduced by Soave also improved the accuracy in the critical properties and the calculations of phase equilibria of hydrocarbons compared with the measurements. The next cubic equation of state is the Peng-Robinson equation introduced in 1976 to improve the Soave-Redlich-Kwong equation of state, where the denominator of the attraction term is replaced with the molar volume Vm times the sum of Vm and the volume correction constant B, plus B times the difference between Vm and B. The alpha function still has the same form, but the polynomial of the eccentric factor omega in the slope parameter has different coefficients, which is denoted by kappa instead of m. As a result, in the correction constants A and B expressed in terms of the critical constants of gas, the constants omega A and omega B become 0.45724 and 0.07780, respectively. The cubic equation of the compressibility factor Z of the substances derived from the Peng-Robinson equations of state tells us that Z cubed, minus 1 minus capital B times Z squared, plus the product of the quantity of capital A minus 2 times capital B minus 3 times capital B squared and Z, minus the quantity of capital A times capital B minus capital B squared minus capital B cubed is equal to 0. Here the definitions of the quantities capital A and capital B are the same as the ones for the Soave-Redlich-Kwong equation. As already mentioned, the maximum and the minimum of the roots of this cubic equation generally corresponds compressibility factors of the substance in its vapor phase and its liquid phase, respectively. The critical compressibility factor Zc derived from this equation in the critical point is equal to 0.307401, which is closer to the values measured for real gases than the value predicted by the Redlich-Kwong equation of state and Soave's improved version of it. The natural logarithm of the fugacity coefficient phi is given by Z minus 1, minus the natural logarithm of the difference between Z and capital B, plus capital A over 2 times square root 2 times capital B, times the natural logarithm of the difference between Z and 1 minus square root 2 times capital B over the sum of Z and 1 plus square root 2 times capital B. The Peng-Robinson equation generally performs better in predicting liquid densities, especially for nonpolar substances, compared to the Soave equation. In 1986 Stryjek and Vera proposed the following modified version of the Peng-Robinson equation of state to extend the range of its applicability to polar substances. Their equation of state still has the same form as the one introduced by Peng and Robinson, but the square root of the alpha function in the attraction term is defined by kappa naught, plus kappa 1 times 1 plus the reduced temperature Tr raised to the power 1 over 2, times 0.7 minus Tr. In this equation kappa naught denotes a cubic polynomial of the eccentric factor omega, and kappa 1 is an adjustable empirical parameter for each pure substance depending on the reduced temperature Tr. Stryjek and Vera provided a table for the values of the parameter kappa 1 for several pure substances that apply at low reduced temperature up to the critical point. If kappa 1 is set to 0 at the reduced temperatures above 0.7, then the equation of state produces better results. The values of omega A and omega B for the modified Peng-Robinson equation are the same as those derived for the original equation of state, but the pressure correction factor A is different due to the application of an improved alpha function. Since the Peng-Robinson equation and the modified equation introduced by Stryjek and Vera has the same form, the cubic equation for the compressibility factor and the expression of the natural logarithm of the fugacity coefficient have the same forms as well. However, the explicit form of the alpha function in the definition of capital A differs in the original and the improved version of the equation of state, which produces different results in the thermodynamic calculations. Stryjek and Vera illustrated the improvement in these results by comparing the deviations in vapor pressure calculated with the Peng-Robinson equation of state seen in the left-hand plot and with their modified equation of state seen in the right-hand plot. The difference between the calculated vapor pressure and the experimental data for several substances given in percentages versus their reduced temperature shows that the improved equation of state produces at least one order smaller deviations in vapor pressure than the original equation of state. Another form improving the Peng-Robinson equation is the Patel-Teja equation of state proposed in 1982, where a third parameter C was introduced in the pressure correction term of the equation of state. The square root of the alpha function is defined by 1 plus a factor f times 1 minus the reduced temperature Tr raised to the power 1 over 2, where f is an empirical parameter specific for the given substance and it is determined by minimizing errors between experimental saturated vapor pressures and those derived from the equation of state. Patel and Teja calculated the factor f for several substances and correlated its value to the acentric factor for nonpolar substances, yielding a quadratic equation in terms of omega. Similarly to the correction constants A and B, the parameter C can also be expressed in terms of the critical constants where the factors omega A, omega B and omega C are determined by applying the same procedure minimizing the error in the saturated vapor pressure as the one applied for the factor F. In this procedure, instead of predicting a fixed value for the critical compressibility factor ZC, it is considered as a substance-specific empirical parameter denoted eta C, that can be adjusted with the error minimizing process and correlated to the acentric factor for nonpolar substances. Then the parameter eta C can also be expressed as a quadratic polynomial of omega. As a result of the error minimization, the following equations are obtained and used to determine omega A, omega B, and omega C. In the first equation omega C is expressed by 1 minus eta C, whereas the second equation states that omega B cubed, plus 2 minus 3 times eta C times omega B squared, plus eta C cubed times omega B, minus eta C cubed is equal to 0. The smallest positive root of this cubic equation gives the factor omega B, which can be substituted into the third equation expressing the factor omega A by 3 times eta C squared, plus 3 times 1 minus 2 times eta C times omega B, plus omega B squared, plus 1 minus 3 times eta C. The Patel-Teja equation of state gives a cubic equation for the compressibility factor Z that states that Z cubed, minus 1 minus capital C times Z squared, plus the quantity of capital A minus capital B minus capital C minus 2 times capital B times capital C minus capital B squared, times Z, minus the quantity of capital A times capital B minus capital B times capital C minus capital B squared times capital C is equal to 0. Here the quantities capital A and capital B have the same definitions as in the case of the Soave-Redlich-Kwong and the Peng-Robinson equations, whereas capital C is defined by the constant C times the pressure P over the gas constant R times the temperature T. This cubic equation has 1 to 3 positive real roots depending upon the number of phases in the system. If a vapor and liquid phase of the substance are present, the smallest root represents the liquid's compressibility factor while the largest root is that of the vapor. The Patel-Teja equation of state provides better results to correlate and predict the thermodynamic properties of many pure substances. In general, the cubic equations of state with 3 parameters have a substance-dependent empirical critical compressibility factor, and as a consequence, they are superior to 2-parameter equations of state in describing liquid densities. Now we present some of the frequently used modifications of the von der Waals equation which results in non-cubic equations of state for real gases or liquids. The motivation of such modifications is based on the fact that the attraction term in the von der Waals equation providing the contribution of the intermolecular forces to the internal energy of substances, while inaccurate at low densities is a useful approximation at high densities. At the same time, the repulsion term gives an inaccurate contribution to the entropy of fluids and real gases, except at densities so low that interactions between 3 or more molecules are negligible. Then, without modifying the attraction term in the equation of state, a better approximation can be introduced in its repulsion term at high densities by applying an improved model of non-interacting rigid spheres for the molecules in substances. The first example of such equations of state was proposed by Guggenheim in 1965, where the denominator in the repulsion term of the equation is written as the molar volume Vm of the gas times 1 minus y raised to the power 4. The parameter y is defined by the volume correction constant B over 4 times Vm, and it is also known as packing fraction since B determines the volume excluded by a given molecule. Guggenheim calculated the virial expansion of the von der Waals equation with the pressure correction constant set to 0, where the multiplier factor of the molar volume can be written as 1 minus 4 times y, and obtained a polynomial expression for the packing fraction y. The same expansion of his modified version of the equation of state with the pressure correction constant set to 0 gave another polynomial of y. The comparison of the expanded equations with the accurate virial expansion obtained in statistical mechanics indicates that the Guggenheim equation of state produces a better approximation of the accurate virial expansion than the von der Waals equation. In the general case, the pressure correction constant A is not 0, and the assumption of the fixed ratio of A to B is also used at the triple point of the substance where all the three states of matter can coexist. If we multiply the equation of state by the molar volume Vm and divide it by the product of the gas constant R and the temperature T, then the ratio of the pressure P times Vm to R times T becomes negligible at the triple point compared to the other terms in the equation. As a result, 1 minus y at the triple point raised to the power minus 4 is equal to the volume correction constant A divided by the product of the molar volume V at the triple point, the gas constant R, and the temperature T at the triple point. Because the volume correction constant A is directly related to the cohesive energy of the liquid, which is the energy required to overcome intermolecular attractions during vaporization, it is proportional to the amount of energy required to vaporize 1 mole of a liquid at a given temperature and pressure. Then the right-hand side can be expressed as the molar energy UM of evaporation of the liquid over the gas constant R times the temperature T. The experimental value of this ratio is equal to 8.56 for argon, which is used to determine Yt, that is the value of the volume correction constant V. At the same time, A also appears in this relation, setting the fraction A over B to a constant. As a result, we obtain the values 0.4963 and 0.18727 for omega A and omega B, respectively. Guggenheim determined several quantities by using his modified equation of state and compared them with the figures obtained from the von der Waals equation and the experimental data for argon. In this table we show the critical compressibility factor Zc, and the ratio of the critical pressure Pc times the molar volume Vm in the liquid phase to the gas constant R times the critical temperature T. For the von der Waals approximation, Zc is 3 over 8, that is 0.375, whereas the Guggenheim equation of state produces the value 0.361, which is somewhat closer to the measured value 0.29 for argon. The ratio of Pc times V sub ml to R times Tc shows a significant improvement from the value 0.141 predicted by the von der Waals equation to the value 0.109 compared with the experimental data given by 0.108. The second table compares the ratios of temperatures and volumes evaluated for the two equations of state with the measured values for argon. By considering the ratio of the volume V in the liquid phase to the critical volume Vc of argon, we see that the von der Waals equation performs better than its modified version. For the experimental value 0.374, the von der Waals equation predicts 0.377, whereas the Guggenheim equation gives only 0.303. This poor performance can be seen for any quantity containing the critical volume, due to the fact that the partial derivative of the volume with respect to the pressure at constant temperature diverges at the critical point. As a result, even a small inaccuracy in the isothermals in the pressure-volume diagram affecting the critical pressure only slightly, has a considerable effect on the predicted value of the critical volume. However, the ratio of the temperature at the triple point to the critical temperature is equal to 0.528 for the Guggenheim equation, which is very close to the measured value 0.557 in comparison with the value 0.350 predicted by the von der Waals equation. The next non-cubic equation of state was introduced by Carnahan and Starling in 1969 with the aim to improve the model of the hard sphere interactions in real gases and fluids. The multiplication factor describing the repulsive effect of the hard sphere model in the first term of their equation of state is given by the ratio of the polynomial 1 plus y squared minus y cubed, to 1 minus y raised to the power 3. Here y still represents the packing fraction of the molecules. This expression for the volume correction term is derived from the approximation of the virial coefficients in the expansion of the compressibility factor also used for the Guggenheim equation. As the expansion in the exact form shows, z can be approximated by the following polynomial with integer coefficients: 1 plus 4 times y, plus 10 times y squared, plus 18 times y cubed, plus 28 times y to 4, plus 40 times y to 5, and so on. Carnahan and Starling wrote this infinite sum as 1 plus the sum of the multiplication factor n squared plus n minus 2, times y raised to the power n minus 1 from n equals 2 to infinity, which is equal to 1 plus the sum of the multiplication factor n squared plus 3 times n, times y to n from n equals 0 to infinity. Because the infinite sums in the right-hand side are derivative forms of the geometric series, they can be expressed in closed form. By manipulating the geometric series, the result for the compressibility factor z can be written as the fraction of the polynomials of y in the modified equation of state. In the Carnahan and Starling equation, the relations between the pressure and volume correction constant A and B, and the critical constants are still described by the same multiplication factor omega A and omega B as in the case of Guggenheim's equation. Nevertheless, the modified equation predicts the value 0.35896 for the critical compressibility factor Zc, which is less than the value obtained from the Guggenheim equation of state, that is closer to the range of the values measured for real gases. This plot shows the compressibility factor for A equals 0, that is for the repulsive part of the von der Waals and the Carnahan and Starling equations of state versus the packing fraction y. The comparison between the curves and the molecular dynamics data represented by the black rectangles illustrates the improvement in the description of the repulsive intermolecular forces in real substances produced by the Carnahan and Starling equation. As a result, the critical constants predicted by this modified equation of state do not differ appreciably from that obtained using the virial expansion in statistical mechanics. The third non-cubic equation of state we present here is proposed by Boublik in 1981, but we show it in a form introduced by Sveda and Kohler 2 years later. The repulsion term in this equation still has the denominator 1 minus y raised to the power 3 as in the case of the previous equation of state, but the cubic polynomial in its numerator contains multiplication factors depending on a parameter alpha. This parameter describes the deviation of the gas molecules from spherical symmetry, where they are treated as hard convex bodies and their repulsive interactions between each other, and alpha is given by the mean radius r star of a hard convex body times its surface area s star over 3 times its volume v star. By definition, alpha is equal to 1 for simple hard spheres, which gives the Carnahan and Starling equation of state. In the hard convex body model, the parameters r star, s star, and v star are determined from the molecular geometry for a given gas or fluid. Different procedures are applied to construct hard convex bodies or shapes for molecules in fluids and N-alkanes. In the case of fluid molecules, the hard convex shape is divided into two parts, a polyhedron or polygon called hard core with several interaction centers determining the appearance of the molecule for its neighbors. The other part is added on the top of this geometric figure as a smoothing hard layer with equal thickness that covers the hard core with its all corners and edges completely. In the case of N-alkanes, the shape of the molecules are assumed to correspond to hard spherocylinders, which look shorter and thicker for curled alkanes and longer and thinner for less curled alkanes. As an illustration, we plotted the reduced temperature versus the reduced density for the vapor-liquid equilibrium of ethane derived from the von der Waals and the Boublik equations of state, where the comparison with the experimental data represented by the black rectangles shows the improvement in the prediction of the thermodynamic properties of ethane produced by the Boublik equation. The performance of this equation of state was evaluated for several nonpolar substances as well and is very satisfactory for the subcritical region and satisfactory for the supercritical region. Now we present the three equations of state that belong to the third group of improved equations of the von der Waals gases and fluids, where both the repulsion term and the attraction term are modified. The first one is derived from perturbed hard chain theory with the acronym SPHCT, which is a synthesis of polymer solution theories and perturbed hard sphere theories. Polymer solution theories lie on the assumption that we can consider a real polymer chain as composed of two components, an ideal chain providing the entropic contribution to the system and a dilute gas of monomers providing the energetic contribution to the system. The core idea of perturbed hard sphere theories is to treat the attractive forces between molecules as a perturbation to the hard sphere potential, which simplifies calculations while still capturing essential fluid behavior. In the simplified perturbed hard chain theory, a simple analytical equation for chain-like molecules interacting with square well potential is derived by replacing the complicated attractive term in the perturbed hard chain theory. One of the several equations of state based on simplified perturbed hard chain theory was proposed by Perät and Prausnitz in 1975 to describe critical equilibria, and we show it in the form introduced by von Pelt, Peters and Ahrens in 1992. For a one-component system, the repulsion term of the SPHCT equation is given by the gas constant R times the temperature T over the molar volume Vm times a volume correction factor equal to 1 plus a constant C times 4 times eta minus 2 times eta squared over the cube of 1 minus eta. In fact, this factor is the generalized version of the Carnahan-Starling model for hard spheres, where eta denotes pi times square root 2 over 6 times V star over Vm, and V star is the close-packed volume per segment in the chain and given by the Avogadro's number Na times the number of segments per molecule S times the cube of the hard sphere diameter d over the square root of 2. The parameter C is equal to 1/3 times the degrees of freedom of one molecule. For spherical molecules there are only 3 translational degrees of freedom and C is equal to 1. For molecules permitting internal vibrations and rotations the value of C is greater than 1, like in the case of N-decane where C is equal to 4.1717. The attraction term in the SPHCT equation of state is equal to minus the R times T over Vm, times Zm times C times V star times Y over the sum of Vm and V star times Y. Here Zm denotes the close packet coordination number of the molecule counting the number of its neighbors in a close packet structure of the molecules of the medium. The quantity Y is defined as the exponential function of the intermolecular potential energy per unit area epsilon times the surface area of the molecule Q over C times the Boltzmann constant K times the temperature T, minus 1. By applying this equation of state, good results can be achieved particularly for vapor pressures and saturated liquid densities of N-alkanes, but its accuracy can decrease near the triple and critical points. In the figure we can see the calculated vapor pressure versus temperature curves of normal alkanes with the carbon number N over the regime where this equation gives reasonable description for alkanes, as shown by the black squares representing experimental data. The next equation of state introduced by Christoforakos and Franck in 1986, and Heilig and Franck brought it into a more general form 3 years later by incorporating several types of the repulsion term based on the Carnahan-Starling hard sphere model into the equation of state. The repulsion term in the equation of state has a generalized volume correction factor given by the ratio of the cubic polynomial of the molar volume Vm with the coefficients f1, f2 and f3 to the cube of the difference between Vm and f0. The attraction term has the pressure correction factor G0, which has different forms for the original and the generalized versions of the equation of state. In the original equation of state this factor describes the effects of a square well potential model of attractive forces between molecules, and it is defined by 4 times beta over Vm, times lambda squares minus 1, times the exponential of the energy epsilon over the Boltzmann constant K times the temperature T minus 1. Here lambda is the relative width of the potential well whereas epsilon characterizes its depths, and beta is a function of the temperature given by a factor depending on the critical temperature Tc of the substance times a ratio of Tc to the temperature T to the power 3 over 10. In the generalized version of the equation of state, G0 is equal to the ratio of capital B to the sum of Vm and capital C over capital B, where capital B and capital C are the second and third virial coefficients of a square well fluid molecules, respectively. In this table we present the explicit forms of the coefficients f0, f1, f2 and f3 of the polynomials of the molar volume in the repulsion term for different equations of states using hard body models of the repulsive intermolecular forces in gases and fluids. The first line in the table shows the coefficients for the Carnahan-Starling 1 fluid model combined with quadratic 1 fluid mixing rules, which are relations used to average the parameters of an equations of taking into account the mixture composition as seen in the definition of the molecular volume parameters beta, beta x, and beta sub ij. Here xi denotes the mole fraction of the component I in the mixture and d sub ij is the average of the molecular diameters of the components I and j. This equation of state has the simplest polynomial expression in the numerator of the volume correction factor as the coefficients are simply beta x raised to different powers. The second model in the table is called Mansouri-Carnahan-Starling left-hand equation of state, in which the effects of increasing differences in sphere size at high densities are taken into account. Here the coefficients contain beta raised to different powers and the molecular volume parameters y1, y2, and y3 describing the mixing rules of the different diameters di and dj of the components I and j. These parameters evidently also depend on the mole fractions xi and the parameter beta sub ij. The third line of the table displays the coefficients for the Boublik hard convex bodies equation of state, which also allows the deviation of the molecular geometry from sphericity, as already seen. The coefficients contain the spherocylinder parameters alpha-1 and alpha-2 characterizing these deviations in the mixture depending on the molar fraction xi, the diameter di, and the volume parameter beta sub ij. The last model shown in the table is the perturbed hard chain theory equation of state, where density-dependent degrees of freedom for rotation and slow vibration are also considered in addition to the anisotropy of shape. As a result, besides the molecular volume parameter beta x, the polynomial coefficients contain the parameters f1 and f2 describing the non-translational density-dependent degrees of the molecules in the mixture. In fact, there is an additional equation of state derived from the chain of rotators theory, another possibility from which the difference between equations of state for hard spheres and hard convex bodies can be derived. The repulsion term in its equation of state can be written as the linear combination of the repulsion terms of the Carnahan-Starling 1 fluid model and the Boublik hard convex bodies model, where the coefficients are 1 minus 1 over 2 times f1 and 1 over 2 times f2. The last equation of state presented here is the Deiters equation of state, which is a semi-empirical expression with several parameters from 1982. In the repulsion term of the equation, Deiters modified the Carnahan-Starling approximation for rigid spheres with the parameter eta such that the compressibility factor derived for that part could have better fit to experimental data by introducing the parameter C0, besides the correction C for non-spherical shape associated with the non-translational degrees of freedom of the molecules. C0 is a constant value obtained from fitting the equation to the argon data, which accounts of soft interactions. The attraction term of the Deiters equation of state also uses the square well intermolecular potential, where a semi-empirical approach is chosen to separate the effects of hard spheres or square well particles at infinite temperature from the effect of point molecules with attractive potential at finite temperature and low density. The later describing the effect of the attractive potential of the point molecules gives the exponential part of the attraction term depending on the reduced temperature T bar given by the parameter C times the temperature T over the pressure correction constant A, which is also equal to C times the Boltzmann constant K times T over the well depth epsilon. The part describing the effect of spheres in the attraction term is expanded in polynomial series since the original equation of state could not be integrated analytically. As a result, the constant H0, the factor gamma denoting 1 minus a constant time the square of C minus 1, and the third term denoted by F sub I plus 1 appear in the equation of state. The third term depending on C and T bar contains the sum of expansion. In order to evaluate the equation of state, the mixing rules for the parameters A, B, and C describing the dependence of the parameters on the composition of the substance have to be known. Deiters also plotted the pressure versus temperature diagram of the systems propane carbon tetrafluoride and butane carbon tetrafluoride to compare the calculated curves for the critical lines with the experimental data represented by the black rectangles. The Deiters equation of state can be used to accurately predict the vapor-liquid properties of binary mixtures. However, at the vapor-liquid critical points, reliable results can only be obtained for mixtures of molecules of similar size from this semi-empiric model.